Check it out now, y'all.
nanoHUB U, online instruction.
Welcome everyone to lecture 3 of week 5 of Atoms to Materials. Today we're going to describe density functional theory. DFT is today the workforce electronic structure calculations in the area of materials. It's by far the most commonly used theory to describe materials behavior. So we're going to introduce it in today's lecture. DFT takes a very different approach, at least in its foundations, with respect to Hartree-Fock and Hartree theory that we've been discussing. So we'll take a step back and think a little bit about how quantum mechanics works and what's at the heart of DFT. So if I have the Hamiltonian that we've been working with, the Born-Oppenheimer Hamiltonian, I know that I have a kinetic energy term, I have an electron-electron interaction term, and the last term that I mentioned I'm showing here is the interaction of the electrons with the ions. Okay, there's one more term that's the ionic-ionic interaction, but that doesn't depend on the electronic wave function. It's just a number, so I'm going to not worry about it. So this last term can be written as a sum over electrons of an external potential that's a function of where the electrons are. Okay, so essentially what happens is the ions generate the potential energy surface on which the electrons live. Okay, so now if we look at this equation, the only term that tells the electrons that they are in iron as opposed to aluminum or a polymer, the only term that's inhomogeneous, that's material specific, is the last term, the external potential term. The first two terms in the equations are completely general and don't depend at all on the system that we're dealing with. Okay, so all the information about the specific aspects of the system is in the external potential. The external potential, interestingly, is a function of 3 dimensions. Okay, and if you remember, the challenge that we have been trying to address throughout this week is the curse of dimensionality. It's the fact that the wave function of the electrons wave functions live in 3n dimensional space. Now, the potential in which the electrons lives only in 3D space. Okay, so that's something interesting to keep in mind. So the way quantum mechanics, the way we've been using it, works is that I start with a 3-dimensional potential. Okay, a potential that's a function of r, the electronic position, lives in 3D. From that potential, I build my Hamiltonian, and when I solve my Hamiltonian, I obtain my wave function and my energy. And the wave function lives in 3n dimensional space. That's the dimensions that's causing us headaches. But I start with the 3D potential, I obtain the wave function and the energy, and from that I can obtain any property that I want. Okay, what DFT is based on a theorem by Hohenberg and Kohn that showed that a way of writing quantum mechanics in a way that it's the electron density, okay, that takes the fundamental central role that the external potential has in the way we have been doing quantum mechanics. So what we're going to show, what they've shown, is that the ground state electron density uniquely determines this external potential. So the Hohenberg-Kohn type of way of doing quantum mechanics is that you start off with the electron density. Okay, the electron density, the ground state electron density, governs, determines the wave function and determines the energy, and from there you can calculate properties, because there's a one-to-one, a unique correspondence between the three-dimensional external potential and the three-dimensional electron density. That's what we will show, we will prove in the next few slides, and that's the Hohenberg and Kohn theorem. Now, if we show that the electron density, the three-dimensional electron density, everything depends on the electron density, then all I need to do is find a three-dimensional electron density and not a 3n-dimensional wave function. So I would avoid the curse of dimensionality problem, and I should be able to solve these equations in a reasonable amount of computational time. So that's what we'll do. So before jumping into the Hohenberg-Kohn theorem, let's think about what electron density means. Let's start with the wave function. This is the full wave function, 3n-dimensional space. We know that the square of the wave function is the probability density. We have multiple atoms, so it's the probability density of finding one electron at R1, another electron at R2, another electron at R3, so on and so forth, up to n, okay, n electrons. Remember, I cannot say the probability of finding electron 1 at R1 or electron 2 at R2, because electrons are indistinguishable, okay? The probability is the probability of finding one electron at this position and another electron at this other position. All right? So, if I integrate over all the equations, okay, if I integrate over all electronic degrees of freedom, if I take the wave function square and integrate over R1, R2, R3, all the way to Rn, what I end up with is with the number of electrons. Okay, so the wave function squared integrated over all of space is going to give me the number of electrons that I have. Okay, all right. Now, what happens if I integrate over all the variables except one? Okay, so I'm going to take the wave function squared and I'm going to integrate over R2, R3. I apologize about that little square, all the way to Rn. Okay, so clearly what I'm left with is a function of R1, which is the variable that I didn't integrate. Of course, I could have done this with R2, R3, or R4, or R35. It doesn't matter. All electrons are the same. All the variables are exchangeable. Remember the symmetry of the wave functions. But the important thing is that if I integrate out all of the electrons, what I get is the probability of finding an electron at position R, regardless of where all the others are. And that's the electron density. If I integrate this function n of R over all of its variable, I get n, of course, right? That's what we got in the first equation. And that shows you that that's the electron density. So we have a definition of the electron density in terms of the wave function, and it involves squaring the wave function and integrating out all variables except for one. Great. So now we're getting closer to start to prove the Hohenberg-Kohn theorem, where we're going to show that the electron density plays a central role in the formulation of quantum mechanics. Before doing that, we're going to show that the contribution of the external potential to the expectation value of the energy is only a function of the electron density. So let's write again the Born-Oppenheimer Hamiltonian, and let's compute the expectation value of the Hamiltonian. I'm going to use T to denote the operator of kinetic energy. I'm going to use U to denote the operator of potential energy between electrons. And the last term is then a sum from I from 1 to n of the wave function sandwiching the external potential. Okay, all right. So let's look at that term in a little bit of detail. I have the full wave function. This is the 3n dimensional space, 3n dimensional wave function times the external potential for electron k times the wave function. What I'm going to do is I'm going to spell that out. I have to integrate over all my variables, x from 1, 2, all the way to n, and I need to integrate the wave function times the potential times the wave function again. Okay, so I'm calculating an expectation value. Now, the potential depends on only one variable, so let's single that out. I have the potential of variable k. What I'm going to do is I'm going to separate my integral. I'm going to integrate k here, okay? And then all the other variables except r sub k are going to be integrated on the second part of the equation, okay? Now, if you look at what we have there, that's the definition of electron density, okay? So what I have is that the expectation value for the external potential is an integral of the external potential times the electron density, okay? And that's what I have there. So this looks like a simple result, but it's very profound, okay? If you see here, this is the full wave function. This lives in 3n dimensional space. This is a very scary beast, okay? This is the wave function that we cannot integrate or do math with. And the expectation value is a functional of the electron density that lives in 3D. That's a very manageable quantity. Okay? Great. Now we're ready to prove and discuss the Hohenberg-Kohn theorem. What the theorem says is that the ground state electron density uniquely determines the external potential of the system, okay? And consequently, because from the external potential I can build my Hamiltonian, and I can solve the Schrödinger equation, and I can find the wave functions and all properties, the ground state electron density uniquely determines the ground state wave function and the ground state energy. So the ground state wave function is a functional of the electron density. The ground state energy is a functional of the electron density, which lives in 3D. So let's prove the theorem. We're going to prove it by contradiction, okay? What we're going to do is make an assumption that the theorem is incorrect, and we're going to see that we arrive at an absurd. So we're going to suppose, okay? We're going to contradict Hohenberg and Kohn. We're going to suppose that there's two different potentials, okay, with the same ground state density, okay? That means that the ground state density would not uniquely determine the potential. So two potentials, same density. So potential 1, okay, I'm going to use subscript 1 to determine my potential 1. It has a ground state wave function, okay, also subscript 1, and it has a density, okay, that I can obtain from the wave function. Potential 2 also has a ground state wave function and a density, and the two densities are the same, okay. That's going to be the assumption that I'm going to make, that I have two potentials that are different that end up with the same ground state density. So let's see what happens. So what happens if I compute the expectation value of Hamiltonian 1 using the ground state wave function corresponding to system 1. Well, the energy that I need to get has to be lower than the energy of Hamiltonian 1 if I use wave function 2. Okay? So, again, wave function 1 is the ground state energy, the lowest possible energy for Hamiltonian 1. So, if I pick any other wave function, the expectation value should be higher. The energy should not be as good as for wave function 1. So if I compute the expectation value for Hamiltonian 1, but using the wave function that belongs to another system, the energy should be bigger. Okay? Great. So I'm going to spell out these two terms. Expectation value of Hamiltonian 1 with its own wave function. I have the kinetic energy term, the potential energy term, and the last term is the external potential that depends only on the density. Okay, not on the wave function, on the density. Now I do the same thing for the second term. So it's Hamiltonian 1, but now I'm using wave function 2. So kinetic energy, electron-electron interaction, and the interaction with the external potential. But remember, we said that the two potentials were the same. So that means that these two terms, the last two terms, are equal to one another. Okay? The contribution of the external potentials are the same for both systems. That means that the first two terms, the kinetic and the potential energy, need to be less when I use wave function 1 than the first two terms when I use wave function 2. Okay? Because the external potential is gone away. So only the homogeneous terms need to capture this difference. Sounds good. Now, what if I do the same thing, but I use Hamiltonian 2? If I use Hamiltonian 2, then of course wave function 2, which is its own ground state wave function, will have lower energy. Okay? So the sign there is changed. I do the same argument that I did before. The external potential cancels, and I get this relationship. So now, the two terms, I get that with wave function 1, the two homogeneous terms, kinetic energy and potential energy between electrons, need to be larger than with wave function 2. Okay? So, again, by making the assumption that two different potentials can lead to the same density, I arrive at an absurd. Okay, these two things cannot be true at the same time. Okay, so I arrive at an absurd proposition. That means that two different potentials cannot lead to the same density. And that means that the theorem is proven. So the ground state electron density uniquely determines the potential. Okay, so that's the Hohenberg and Kohn theorem. Let's sum up what Hohenberg and Kohn found. What their theorem shows is that the ground state wave function is a function of the electron density. Okay, so if I know the ground state electron density as a function of position, n sub r, I can, in principle, obtain the wave function, the 3D full wave function, 3ND full wave function from it. Now, of course, then it follows that the ground state energy is also a functional of the ground state density. Okay, so if I know the ground state electronic density, in principle, the ground state energy is a function of this density. Okay, you can show that it has variational properties in the sense that if I can write this energy functional of the electron density, then my job is simply to find the electron density that minimizes the energy functional. Okay, so the ground state the ground state electron density will give an energy that's lower than the energy given by any other electron density in that system. Now, the challenge is that we don't know what this functional is. The challenge is that we know that the energy is a functional of the electron density, but we don't know this functional exactly. So there's multiple ways of solving this DFT problem. We're going to describe very briefly the Kohn-Sham approach, okay, and the Kohn-Sham equations. And so just to sum up what the problem is finding the energy functional, okay, or a good approximation to the energy functional, which is what we're going to end up doing. So far the theory is exact, okay? The energy is a functional of the electron density, but we don't know that functional. So how can we solve that problem, okay? I know I can write the total energy will have multiple components: kinetic energy, electron-electron interaction, and the interaction of the electrons with the external potential. That last piece is easy to write, and we've shown that you can write it this way. It's a very simple functional of the electron density. The challenge is writing the kinetic and the electron-electron interaction, and if you remember, that has all the correlations. That's the challenging part. So what Kohn and Sham did is they brought back the idea of single electron orbitals, and what we're going to do is write this term F, okay, in terms of a simple functional that we know, plus we're going to sweep under the rug everything we don't know about correlations and about exchange into one function that then we'll try to parameterize. So what they did is, for the kinetic energy contribution to this, is they consider a set of non-interacting electrons, okay? So assume you have a set of non-interacting electrons with the density n of r, and then I know that the solution is going to be a set of independent orbitals, okay? So the kinetic energy in that term, these electrons don't interact. The kinetic energy for the non-interacting case, I know I can write in terms of individual orbitals, okay? And so I know that that's going to be a functional of this electron density that I have, and I'm going to call that functional T, that's kinetic energy T of the single particle system, okay, the non-interacting part. Now, of course, in the real systems, the correlations will change the kinetic energy, and I'm going to call that unknown term, okay, T sub C, that comes from correlations, okay. Now, I don't know what the single particle kinetic energy functional is, but I know it exists, okay, so I can formally write it that way. Now, for the electron-electron interaction, what Kohn and Sham did is also similar. They wrote it as a sum of something that we know how to write plus corrections that we don't know exactly. The part that we know how to write is the Hartree term, okay? So if you remember from Hartree, this is the way electron-electron interaction is done, in a mean field kind of way. And that's a functional also of the electron density from these orbitals, okay, written in terms of the orbitals. So I'm going to call that UH, U of Hartree. And then for the real system, I have an extra term that's the exchange and correlation contribution to the electron-electron interaction, that, if you remember, Hartree assumes a simple product of orbitals, no exchange, and no correlation. So everything that's more complicated than Hartree is swept into this functional, okay? So at the end of the day, I can write my total energy functional, as a sum of the kinetic energy of the single particle system, a Hartree type electron-electron potential energy, the external potential. So all these terms, these and these I can calculate. These I know that I can compute. The first one, the kinetic energy, I can compute in terms of the orbitals. And everything I don't know, okay, was put here, okay, in the exchange and correlation potential. So it's just rearranging terms, okay, and putting everything that's unknown into a single term. So it looks like we haven't made any progress, just rearrange the terms. However, when we look at this energy expression, it looks exactly like the Hartree equations, okay? But instead of having, in Hartree, having just the external potential, now I have the external potential includes the exchange and correlation potential, okay? So if I take the Hartree equations and replace external potential with external potential plus exchange and correlation, then I have these Kohn-Sham equations that are with the that satisfy DFT. I know what the exact solution for Hartree is, so I can use that to solve the Kohn-Sham equations, okay? And that's the trick, is to sweep everything we don't know into one term that looks like an effective external potential. The challenge is still back when the Kohn-Sham equations were derived, that we need good approximations for that exchange and correlation potential, okay? So the remaining issues that we'll discuss very briefly in the next few slides is how do we approximate this exchange and correlation functional that we know it exists, okay? So, and if we knew the exact value, then the theory would be exact. Unfortunately, up to this point, we don't know it. And there's some few numerical issues that you have to be aware when you run or read papers about DFT. And the main two are the following. You're going to use a basis set, okay, a set of functions to describe these Kohn-Sham orbitals, okay, and the appropriateness, how big this basis set is, then affects the accuracy of your calculations. And these basis sets could be plane waves or could be localized basis sets. And also, we use pseudopotentials to replace core electrons, okay? Most of the time when we do DFT calculations, not always, you replace the electrons that are near the core with what's called a pseudopotential that takes care, because those electrons, low energy electrons, are very inert. You know, they don't distort, they don't participate in bonding. So we put them in the potential and make sure that the electrons, the outermost electrons, see these electrons in the appropriate way. Those are called pseudopotentials. Okay, so let's talk a little bit about exchange and correlation functionals. As we just discussed, we don't know what the form of these functionals are, but in the 80s, okay, people developed very, very good approximations. And if you look at the use of density functional theory for electronic structure calculations in the 80s, it really takes off and becomes extremely popular. It's very widely used, and that's because in those years people developed accurate and good predictive functions for the exchange and correlation function. So the exchange and correlation functional is a function of the electron density that gives me all the contributions of exchange and correlation to the total energy. And there's the exchange and correlation functionals that we use today can be divided in two categories. The first category is called local density approximation, and what it assumes is that the exchange and correlation functional is simply an integral over space of a function that depends only on the local density at that point, okay? The way this is constructed is you break up the exchange and correlation into two terms. For the exchange term, there's an exact equation for non-interacting. If I have a homogeneous non-interacting electron gas, there's an analytical solution. You can find that, again, for a homogeneous system, the exchange energy goes as the density to the power 4/3, okay? So what we assume in LDA is that the exchange part of the exchange and correlation potential is an integral over all of space of the local density at that point to the power 4/3. Okay, so this ignores, the solution works for the homogeneous gas with no gradients. So this ignores any sort of effect of gradients or variations in the density, and it should work okay as long as the density doesn't vary very abruptly in space. That's the exchange. The correlation, there's no analytical solution, but Bernie Alder and David Sepperly performed very expensive quantum Monte Carlo simulations and obtained numerical values for this correlation, also for the homogeneous gas. And there's different parameterizations of from this data that we use today. Okay, so that's LDA, local density approximation. The next level up is what's called GGA, generalized gradient approximation. And here, the exchange and correlation functional depends, it's an integral over space of some function of the local density, just like LDA, plus a function of the gradient of the density. So there's gradient corrections that account for variations of the densities. And these GGA functionals work a little bit better than LDA, especially for things like defects and where you would expect, because there's larger variations of, faster variations of density. There's different parameterizations. Okay, one that's very popular is called PBE from '96, but there's others. Okay, here's different ones, and a class of simulations that are called hyper GGA. Okay, mix a little bit of GGA with exact exchange from Hartree-Fock. So if you remember in Hartree-Fock, we describe exchange exactly with the Slater determinants. So some of these descriptions, what they do is they compute the exact exchange with Hartree-Fock, okay, with the Slater determinant, and they mix in some of that exact exchange to with the GGA exchange and correlation. Those are called hybrid methods. Okay, they're not strictly speaking DFT, but they do they're useful under some circumstances. Okay, so that summarizes our very, very quick and brief description of DFT. If you're interested in learning more, there's many resources online. Of course, there's many other books and papers, and these are some some good references that I would recommend. This paper in Review of Modern Physics is very useful and very general. Okay, despite the title that seems very narrow, this is an freely available online resource that's very useful. And more on the application side of things, this paper by people at Sandia is a primer to DFT calculations. So it walks user through the type of things that you have to check in order to design meaningful simulations, both numerical and physics. And it's a very useful paper. I would recommend it to everyone. There's also, as you know, a variety of simulation tools in nanoHUB that use DFT. You've already used Sequest and Quantum Espresso. We also have a Binet, and those are good resources as well. And there's in nanoHUB, there's a lecture, a research lecture by Peter Schultz, who's a collaborator of ours from Sandia National Labs, and where he discusses whether the band gap issue with DFT is really a limitation of the theory or not. And he makes the point very well, I think, of you have to ask DFT the right questions if you want to get the right answers. Okay, so a very valuable and interesting lecture. With that, I'll finish. And thank you very much.